Hey everyone, my name is Trent Kelly, and this is my first attempt at D209 data mining and table of contents. So we're going to describe the purpose of this data mining report, define one goal of the data analysis, explain the reasons for your chosen classification method, perform data preparation for the chosen data, and perform the data analysis and report on the results, summarize data analysis. So starting out, describe the purpose, propose one question relevant to organizational situation that you will answer using the following classification methods. So the classification method I'm using is KNN, and I'll be using KNN, and as defined, it creates a set of decision boundaries. And so, and I have a picture that kind of helps identify this. But basically, if we have like a scatter plot and we have like three points, we have like three that are known and labeled, and then we have one that's unlabeled. What KNN is going to do is, depending on our KNN number, it's going to help assign or predict or learn what that unlabeled data point is based on distance. And so my research question is going to be, can our model accurately predict patients with high blood pressure using k-nearest neighbors? And define one goal. The goal is that my analysis aims to determine if we can build a model that accurately predicts patients with high blood pressure. Explain how the classification method you chose analyzes the selected data set. And so I selected KNN based on these benefits, so it's easy to understand. It's non-parametric algorithm, is a non-parametric algorithm, so it doesn't have strict assumptions. No training steps are required. And since it doesn't need training on data, data points can be easily added. And so, as mentioned above, so KNN just is used to predict unlabeled data, and then it comes to an agreement based on distance on what the unlabeled data point should be labeled. And so I selected it because it's easy to implement, and it has an easy time at labeling unlearned test data. For my expected outcome, I expect to create a model that accurately predicts individuals with high blood pressure with at least 95% accuracy without under or overfitting. Summarize one assumption. So the data is in feature space, which means data in feature space can be measured by distance metrics such as Manhattan and Euclidean. And so the way you think of this, Manhattan, think of it just like a city block. So you're navigating a city, and so you have to go down one block, up 2 blocks, etc. Euclidean is going to be using something similar to Pythagorean theorem. And so you think of it as like a right triangle, and that's how it navigates distances. And the calculation is similar. And these are the libraries I utilize with the descriptions on why I use them. I describe one data preprocessing goal relevant to the classification method. So data preprocessing is kind of an umbrella, and I didn't feel it was appropriate just to select one, so I kind of have a few in here that I did. So data cleaning first. So we renamed some of the variables. We identified duplicates. We look for outliers, which I use several different techniques, which I go into later on, which I kind of went down a rabbit hole on and deep dive on it because I was learning a lot. So just went down a rabbit hole on it. And then looking for null values, which is extremely important with the model that we're creating. And then one hot encoding, and so we're taking categorical variables that cannot be binary, so they can't have just one or two outcomes, and they'll be hot encoded, one hot encoded. This also changes the true to false to binary representation of the categorical variables. So if they are yes or no or true or false, one hot encoding automatically changes them to a binary function. And we also need to do some renaming, which I'll outline later. And so the importance of one hot encoding is, if we have a categorical variable that, like take gender, for this, medical set that I'm using, it has male, female, and non-binary. You can't make that 1, 2, and 3, because then that implies that there's a hierarchy or level importance between male, female, and non-binary, depending on which one you get. And that's not how that data is supposed to be viewed or looked at. So one-hot encoding essentially assigns each one of them their own name. And that way that we can pick them out and still kind of number them, but they're not numbered in level of importance. They're numbered for categorizing. And then we standardize the data. And so what we did is we did some mean centering. So we transformed data, we'll have a mean of 0, and then scaled the data, which each data point is then divided by the standard deviation and makes the scale of the data 1. So this is very important because KNN finds a predefined number of training samples closest to the distance to the new point and predicts the label from these. If the feature variables have different scales, then the KNN will be less accurate. So if we're not operating off the same playing field of each variable, and each variable has its own unique level or classification, your model is going to be very inaccurate. So what standardizing and scaling does is it brings everything down to a relative scale. That way, as much as we can make equal, we're making equal. And brings all numerical variables into a common feature space. And identify the initial dataset variables that we use to perform the analysis for classification question, and classify each variable as continuous or categorical. So according to the PowerPoint, this is supposed to be numeric, not continuous, so they're labeled as numeric rather than continuous. But my dependent variable is going to be high blood pressure, and these are the independent variables. So these are the categorical variables, and then the numeric predictor variables that I've selected. Explain each of the steps, use compare the data for analysis, identify the code for each step. So first, we're going to load the data, view the data, evaluate the data structure and types, remove all null values, changing data types, standardizing, scaling the numeric data, one-hot encoding, checking for outliers for standardized data. We've already explained all of that in the above. And loading and viewing, we have to do it below because that's when we're going to be utilizing our code. Plotting the data versus standardized data to evaluate data representation, which we'll see in a minute. Select k-best and samples versus feature, which we will see later. Running the model against trained and test data to determine accuracy. So here are the libraries I'm importing. And this is the CSV that we're using, the medical data set, the medical raw data CSV. And just importing it, looking at the head, which pulls in the first 5. And here I'm just looking at the data types to see if we need to change anything, looking for null values. And renaming, so we're renaming these items based on the data dictionary. And so we did a forward fill on the NA values. I played around with doing forward fill and back fill, and I felt the forward fill is more appropriate because when we forward fill, it fills the NA in age, but if we backfill, it will throw an error to an NA in age, but there will be an NA in soft drink. So soft drink still has one null value in the first row because of the forward fill, but if we backfill, age will have a null value in the last column. And it is very important that our learning model has 0 null values. And so since we forward filled and that took care of the age missing, we still had the missing row or data point in soft drink. So I just took that and made it a no. Since it's so small, you could have went either way, and I don't think it would have mattered. I could change this to a yes, and I don't think overall it would have changed the analysis. And so overweight, there were some that had this 0.709, so that was changed to a 1. Again, you could have made that a 0, but I felt since there is some data in here and there was not further clarification in the data dictionary on what that was, I just made it a 1. And so here are or here is the fixed data set. And so I noticed that we had some different data types in here. So we are going to change those. So these are the ones specifically that need to be changed, and we're just converting them to an integer. And here is just highlighting that the soft drink, we had a null value in the zero column, zero row, and then after we fixed it, that is gone. And we had to rename associate's degree and specifically get rid of the apostrophe. That was causing issues later on, so I just renamed it to associate degree because that apostrophe was just causing problems. And here's a standardization of the numeric predictor variables. So just utilizing z-score, and to rename them, just so I know which is which, we just put underscore z. And just to see what it looks like using the describe function. So before standardizing, this is what it looks like, and then after standardizing, this is what it looks like. And here's our one-hot encoding, so it's just taking the categorical variables and splitting them out like we discussed earlier, and then taking our numeric columns and then adding them together. So we create one new data frame where it has all of this together. And then we're just taking a look at it, seeing what it looks like now, making sure everything is being split up. And we do have one dummy variable being dropped. I felt like there was conflicting information in the resources on whether to do this or not. So I may get dinged on it, but if I recall, there was one source saying to include all, and then I think in the PowerPoint, could be wrong, set to drop. So that's what that is. But to change that to where nothing is dropped, you just put in false. And identifying outliers through calculation, you can take the variable's maximum subtracted by the mean and then divided by the standard deviation. Since we have standardized our data, we can use the following code to fully analyze outliers. And so this is where I kind of went down on a deep dive. So I was just looking at things initially through the describe function to see what everything looked like, to look for outliers. And typically what I would do is just look at the category and determine what would be reasonable for that. So looking for like children, you can't have like -5 children, and age, you can't be -3, and then 150 beyond the reasonable expectation of human lifespan. So that's typically what I'll do. And then looking at your quartile ranges, seeing how that revolves around the mean and the standard deviation around the mean. But since we have everything standardized, I was looking at outliers that are 3 above and 3 below the standard deviation of the mean. And so with income, this tells me that we have 63 columns or 146 rows that are above or below the standard deviated mean. Vitamin D levels, there are 500. With initial days, there are 0. Children, we have 210 rows, 8 rows for doc visits, 33 rows for full meals eaten. Vitamin D supplement, 70 rows. You get the point. So I took all of those that we identified that there were outliers, that was at least showing us that we had a certain amount there, and then so I looked at them to see how far above the standard mean they were, and also to understand if it was reasonable for these variables to have these kind of quote outliers, 3 above or 3 below the standard deviated mean. And all of the, long story short, all of the variables, they can be reasonably explained as to why they have, they're above 3 deviated norm. So I didn't change anything with outliers because I could articulate why they were so high, and it's just the nature of the variables themselves. So vitamin D supplements, that may be 7 above the standardized mean, standard deviated mean, but that's possible, and that's certainly reasonable that somebody could be taking that high of a supplement, or their vitamin D levels can be that high. So all the variables, I felt it was respective to the variable type, and it wasn't somebody misclassifying something and creating an unintentional outlier. I feel like these are all respective to the data itself, so I didn't change anything with the outliers. And further outlier analysis, I just plotted everything out just so I could look at it, and then I plotted it against the z-scored standardized data just to see what it was doing. So with pretty much everything, you're going to see 2 different plots. That's all that is, just looking for outliers, see how the data looks, how it's dispersed. There's a lot. All right, so getting into k-neighbor stuff, selecting k-best. And so what this is doing, what this code is doing and allowing us to do is it's taking all the variables that we had with our explanatory variable and looking at the p-value and selecting our explanatory variables or predictive variables based on their p-value. And so we want ones that are 0.05 or less. And so that's what it's doing for us at selecting these. And then so from here, we're going to select these and use them for our model. Here's the clean data set. I've got the original that I cleaned, and then I have the regression that I used with the one-hot encoding. And then looking to see if we have any VIF issues, which we don't with what we have selected. So it's looking for multicollinearity. And here we are splitting our data up into train and test. So X train, X test, Y train, Y test. And so it's splitting it into 80-20. Train sizes versus tests, and then our random state is just an RNG. So this doesn't matter. It can be anything you want. It just when you are trying to reproduce the model, you have to use the same random state for the RNG. And according to data science, for highly complex data sets where a neural network model needs to learn about many nonlinear relationships within the data, more training records would recommend for 75 to 90% of the original data. For smaller or less complex data sets, one should retain sufficient records for accurate assessment, 50 to 67% of the data. The random state doesn't matter, it just sets a number for RNG, so it can be reproduced. It can be of any value. So even though that I saw this, I just left it at the recommended 80-20 per the PowerPoint. And then looking at the actual X train and then the shape. And exporting the trains and tests to CSV files. And so describe the analysis technique used to appropriately analyze the data, include screenshots of the intermediate calculations you performed. So I was a little unclear about this one. So KNN is the only calculation that I utilized. I reviewed the scikit-learn site, and with how I prepared everything, it was just a little different. So the only algorithm that I used was KNN. And this kind of further illustrates KNN. So depending on your KN number, you may use the solid circle. So we're going to have, since we have two triangles, the label for this is going to be 2. And then the further we go out, so if we go out to, say, let's see, K3, K5, so then the further we go out, we're going to start including additional labeled data points in order to predict this labeled point, this data point. And so this is telling us, based on an array of 1 to 29, and telling us what our ideal KN number is going to be. So it advised that 23 is the ideal number. And so we're doing, this is all based off of grid search, and our cross-validation is 10. So, and then I also put in, because this really took a long time to run, so I put in a timer on it to see how long it takes to run, and it takes 17 seconds to run. And I believe you could get this down by, like changing your K number and your cross-validation number. You could get that time down. If you need something more efficient, you could reduce that time. But, and then calculating the sensitivity and specificity, which we'll come back to, and using our recommended K number of 23. This will give us our accuracy score of our model and give us the confusion matrix, which tells us the true positives and negatives and all of that. So from this, I put it in here, so just for illustrative purposes to help me understand. So that's that. And looking at training accuracy versus testing accuracy. So this is good that they are very similar. And I would say statistically they are identical. And the accuracy score for the model itself, which I don't know even, is that a duplicate? Basically the same thing as that. Yes. Our AUC, so the area under the curve, is 0.85, which we will come back to, and then our classification report, which gives us kind of the sensitivity, specificity, and a combination of the yes and no's. And this is a model complexity plot. So what's happening here is as the K increases, the test versus train accuracy is going to change. And so as of right now, and it's plots out several different ones, so it adds in increasingly higher K values. And so as we get further down, we see that, several things are happening. So the accuracy is dropping of our training accuracy, and the testing accuracy is increasing. And then eventually it's going to hopefully establish an equilibrium point where we have settled on our K value of 23. And so it keeps adding in larger K values. And then finally we get this. So this indicates that both accuracies are running parallel. And I wonder if I could put a line through here, if this would be considered an asymptote. And with model complexities, as the KNN is smaller, the accuracy will be further apart. But as the model becomes less complex with more KNN, then the two accuracies should become close to one another. And so these are running parallel with one another. And so from data camp, they indicated that the larger the K, the smoother the decision boundary. It's a less complex model. The smaller K, more complex model can lead to overfitting. It can be sensitive to noise in the data rather than reflecting the general trends in the data. So the fewer variables you have, the more complex the model becomes and is at risk of being overfitted. And it seems counterintuitive, but the more variables you have, the less complicated it is. And the fewer variables you have, the more complex it becomes. And each has their own offset. So smaller K, you can have overfitting. Larger K, you can potentially have underfitting. Explain the accuracy and the area under the curve. So for accuracy, we look at the training for testing data. We compare how well the model does on known trained data and then test the model using the test data. If we overfit, then the model will have a high accuracy regarding the training data, but a low accuracy with the testing data. And opposite, if the model is underfitted, it will score poorly on both training and test. So the accuracy measurements, so the training accuracy we got is 0.843 and the testing accuracy is 0.835, which these are virtually the same to me. The AUC is an indicator of the model's discriminatory capability to differentiate between positive and negative classes, and it provides a metric that indicates how well the model performed versus a random selection of 0.5 chance. A perfect model would be a 1, whereas a random chance would be 0.5. So in our case, it's 85, and make it 86%. So it is only 36% better than a random chance or random choice. And that's what the AUC does, is it kind of plots it against random chance and tells you how well your model is compared to something being completely random. And again, with our training accuracy and testing accuracy, discuss the results and implications. So for my results, I conducted feature selection through select K-best to identify the best K features. This selects a feature to use in a tuned model that is based on ideal p-values, which we went over above. Hyperparameterization. We determine that the best K neighbors through grid search and cross-validation. That tells us the ideal number that we got to is 23. When evaluating models like this, it's not about a single indicator. Just like when we went over logistic and linear regression models, it's all about the totality of the model itself. So we're not only looking at the information that the model is giving us, but we also need to consider the variables themselves, external considerations, and to evaluate the success or failure of the model itself. So with external considerations, how is the data collected? How much of the data do we have? How is the data weighted? When looking at success versus failure, I'm looking at how successful the model is at predictions on data it has never seen before. So the test data set versus how it compares to random chance, or the training data. The AUC helps us with this, and the AUC is 86%, which tells us that it's 36% better than pure random chance. Also looking at training accuracy versus testing, the numbers are statistically the same. This is an indicator that the model performs well on both training and test data, and this tells me that the model is not over or underfitted for our purposes. When comparing the confusion matrix against the sensitivity and specificity, I'm happy with the 0.98, whether that is legitimate, which accurately identifies negatives, but the sensitivity is at 61%. So this tells me it lacks sufficient capability to detect true positives. However, it is good at detecting true negatives. So I don't think the model is completely bust. I mean, for our research question, we would have to go to our alternative hypothesis. We didn't have one, it wasn't required. But we did not have positive accuracy. We had accuracy and negative values. So the model itself still could be used. So if we had like a research question or research study that was looking to exclude people with high blood pressure, I would say this model would succeed in that fashion because it's really good at identifying negative high blood pressure, which come back to that. So how does the model compare to the precision score and recall score? When we compare sensitivity and specificity to precision and recall, the values are closely related to the metrics, and we're seeing somewhat similar results. So sensitivity was 0.61, which tells us the model's capacity to predict true positives accurately, and the recall is very similar to sensitivity. It's 0.99 for predicting negatives, but is at 0.61 for predicting true positives and 0.99 for actual negatives. Specificity was 0.98, which tells us the model's capacity to accurately predict true negatives. And I do want to point out that 0.61 for predicting true positives, this is in line with the sensitivity, so that's good. And I would say with our true negatives, that's in line with our specificity, which tells us the true negatives, which that's what that's for. Precision, the precision is 0.79 for predicting true negatives. It's lower than the sensitivity, but what is more concerning is that the 0.97 rate of predicting true positives. So this is not in line with other metrics we have uncovered, thus far: sensitivity, recall, specificity. So I would not trust the specific metric when analyzing the utility of the model. So what I mean by that is, even though that the precision says that it has a 97% rate of predicting true positives, we have other indicators that conversely say that the model is not good at predicting true positives. So that precision specifically, I wouldn't just trust the true positive prediction based on precision alone. I would factor in all of our other metrics with that decision. Discuss one limitation to your data analysis. When we look at the dispersion of data and the predictive question of who has blood pressure or not, I would like to have equal data points for both yes and no. So I would like to have just as many people with high blood pressure and just as many people without. So we have, and the reason that's important is because our model is really good at predicting true negatives, which we have an abundance of true negative data, and we have several thousands less of true positives. So that could be potentially why the model is better at predicting no's versus yes. And this illustrates that. My recommended course of action would be, so if the model requires patients to be screened, and we want them to be screened out for not having high blood pressure, the model would succeed at that, but it would be poor at outlining true positives. So it wouldn't be good if that's the use case for the model. So what I'd recommend is either switching or using this model for a different methodology. So screening people out of studies that don't have high blood pressure, and also collecting more data so we can equalize the parameters, and that way we know that if we have equal data for high and low, or yes or no, that we can apply more correlative thinking to the model itself. And so here's the demonstration and my sources, and that concludes my presentation, and I look forward to feedback, and thank you for your time.